Intermediate Algebra, Section 11.1, Sequences and Series. A sequence is quite simply an ordered list, and here I have an example of 2, 4, 8 with an ellipsis, meaning it continues on in this pattern. And if we look closely, each one of the previous numbers appears to be doubling. 2 doubled is 4, 4 times 2 doubled is 8, 8 times 2 is 16, and so on. And we have some definitions for sequences. There are two types of sequences. The first one is an infinite is a function having for its domain a set of natural numbers 1, 2, 3, continuing on with an infinite number of terms. A finite sequence is a function having for its domain a set of natural numbers where we know what the last term number is. It's continuing, but we know that there's, say, 100 terms, whereas here with the ellipsis and nothing past it is continuing infinitely. Some sequences will give us rules, and we'll look at a couple of examples. Given the nth term in a sequence has the following rule, they're asking us to find the first 3 terms, and that's designated by the subscript of these term numbers. So the first term in this sequence will be a to the first, or a sub 1, and replacing n with 1, following order of operations, multiply gives us 4, minus 1 is 3. The second term will be 4 times n, and our subscript and term number is 2. Multiply first, 4 times 2 is 8, minus 1 gives us 7, and the third term would be replacing n with a 3. Multiplying before subtracting, we have a 12 minus 1 is 11. So the first 3 terms in this sequence are the following. Here we have a little more complicated rule for a sequence. They're asking us to determine the first term of this sequence, and they're indicating that with a subscript of 1, so we will replace n with 1 and simplify. Following order of operations, we simplify inside the parenthesis first. Division has priority over subtraction. 1 divided by 1 is 1. 1 minus 1 is 0, and 0 to the second power is 0. So this particular sequence starts out with 0, and then they're asking us for the 10th term. So we will replace n with 10 and simplify. We have 1/10 when we do our division. 1 minus 1/10 leaves 9/10. That is going to be squared, which results in 81 hundredths. There are times when they will give us a sequence, but there's times when here they give us the rule, but we will have the opposite of that. They have the sequence mapped out for us, and they're asking us to determine what the general rule, similar to what we did, only in reverse. So it's helpful if we write the term number. This is the first, the second, the third, and the fourth, and determine what they're doing to that term number to generate this sequence. There is no unique answer, but it's best oftentimes to just keep it simple without adding a lot of extra steps that may cause confusion down the road. So for this first example, 3 is the result of 1 times 3, 2 times 3 is 6, 3 times 3 is 9, 4 times 3 is 12. So for a general term, or the a to the nth term, one solution would be to generate this sequence would be to have 3 times n. And it's best to use your rule and verify that it does work for the sequence given. In this next example, the same strategy. This is our first term, our second, third, and fourth. When we're generating our generic term, then what's happening to our term number? Well, the term number is the first in each one of these terms, and the second number is just one more than the term number in each one of these cases, and they're being multiplied together. So a possible expression for the general or nth term for this example would be n, and that's again the 1, 2, 3, 4 times one more than n, which we will express as the quantity n plus 1. In this next example, we have alternating signs, but again the strategy is to help us with the term number is to identify each one of those terms. And if we start out with, don't worry about the negatives to begin with. The first term is 2, the next term is double, the next term is doubling that, and the next one is doubling that. These look like powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, but we have this alternating sign, so we have to deal with that. There's multiple ways of doing that, but one would be simply taking our base as -2 to the nth power. When we take a negative to an odd power, it's negative, so that would be the case for our first and third. And when we take a negative quantity to an even power, it becomes positive. And if you check, -2 to the second power does give us 4. -2 to the fourth power, 4 negatives multiplied together would give us 16. And as I said, there is no one unique way of representing these. This is one that happens to work though.